Remember the sheer frustration of searching for something online, typing in what you thought were the perfect keywords, only to get a list of utterly irrelevant links? I swear, I once spent 20 minutes trying to find a specific recipe for spicy chicken and just kept landing on fast food menus. We've all been there, right? Endlessly refining our queries, feeling like the internet just wasn't speaking our language. But what if I told you that era of keyword guessing is rapidly fading, replaced by something far more intelligent? Today we're taking a deep dive into something truly transformative: semantic optimization for AI. We're going to explore how the new generation of search engines, powered by artificial intelligence, is fundamentally changing not just how we find information, but how information itself is structured and understood. It's not just about matching isolated words anymore. It's about grasping the deep intrinsic meaning behind those words.
Exactly. And our mission today is to unpack this revolution in search for you, our curious listener. We'll journey through the underlying technologies that make this possible, think vector databases and embeddings, to reveal how large language models are shaping the very fabric of our search results. What's fascinating, though, is that this cutting-edge tech actually draws on timeless wisdom from library science, proving some ancient principles are more relevant than ever. Ultimately, we want to show you why understanding semantic optimization isn't just a niche topic for tech enthusiasts. It's becoming a crucial survival skill for anyone navigating the modern web, whether you're a content creator, a business owner, or simply someone who wants to find answers more effectively.
Yeah, that's a great point. We've gathered some truly fascinating sources for this deep dive. We've got technical explanations of semantic search, foundational principles from information science, even insights into how this impacts fighting misinformation. We'll connect these dots, hopefully giving you a shortcut to being truly well-informed about where search is headed. So let's begin this journey and unpack the meaning behind the revolution.
The great leap from keywords to meaning.
So let's cast our minds back a bit and set the stage. Historically, when we typed a query into a search engine, how did computers understand what we were looking for? It felt very much like a simple, literal word matching game, didn't it?
You're absolutely right. For a very long time, it was exactly that. A highly literal, almost simplistic process. Think about conventional databases. They store information in rigidly structured fields, categorized by very specific attributes like file format, creation date, or maybe manually applied tags. This system works incredibly well for highly structured data, where every piece of information has its designated, predictable place. But then you look at the internet, and as you know, it's absolutely overflowing with unstructured content. Think of all the vast amounts of text documents, images, audio files, videos uploaded every single minute. The sheer volume of this messy, unstructured data compared to the neat, structured kind is just, well, it's staggering. And this creates what we call the semantic gap.
The semantic gap, okay.
Yeah, it's this enormous disconnect between how computers physically store raw data, just bits and bytes, and how humans perceive and understand its inherent meaning, its true context, its intent. To give you a more relatable analogy, imagine stepping into a vast, sprawling library where all the books are organized only by their physical size or maybe the color of their spine.
Right, not by what they're actually about.
Exactly. There's no system to connect them by their actual content, their themes, or their authors. You struggle immensely to find, say, sci-fi movies about space just by searching for the exact word space. You'd probably end up with anything that happened to contain that literal word, whether it's a book on physical outer space, a financial space, or even just a blank space on a page. The system is essentially blind to the meaning you're trying to convey.
And here's where the problem really compounds, isn't it? Human language itself is just, well, it's full of ambiguity. We understand nuances and subtleties that a machine simply can't grasp without a lot of help. We use context all the time without even thinking about it.
Precisely. Ambiguity, far from being a flaw in human language, is actually one of its most fascinating features. It gives our language incredible flexibility, richness, even poetic depth. But for machines, it's been a colossal obstacle, a constant source of misunderstanding. Consider that deceptively simple word, bank. If you just type bank into a traditional search engine, what do you mean?
Right. Riverbank,
Right.
money bank, data bank.
Exactly. Are you looking for a financial institution, the edge of a river, a data repository, or perhaps even a maneuver an airplane makes? Or take the classic example, he saw the man with the binoculars, who actually possesses the binoculars.
Is he using them or is the man carrying them?
Right. Humans effortlessly use a complex interplay of context, prior knowledge, maybe even nonverbal cues if we were talking face to face, to resolve these ambiguities instantly and almost unconsciously. Computers, on their own, simply cannot do that naturally.
So what's the practical impact of this inherent ambiguity for something like search engine optimization or just finding reliable information?
Yeah.
What does this mean for us, the users trying to get answers?
Well, this pervasive ambiguity generates what's termed a cost of uncertainty for anyone trying to optimize content for search, or indeed for anyone just trying to get accurate answers. If a search algorithm, even a relatively sophisticated one, can't truly decipher the precise intent behind a user's query, it's forced to cast an incredibly wide net, trying to cover all possible meanings.
Hedging its bets.
Exactly. This inevitably dilutes the relevance of the results, leading to user frustration, and ultimately sends negative signals back to the search engine itself about the quality of its own results. So, for a content creator, optimizing for a term like bank without providing crystal clear context is quite literally a shot in the dark. You're hoping to hit the right target, but lacking the precision to do so consistently.
It really sounds like words alone just aren't enough. If meaning is the absolute key, then how on earth do we teach computers to understand that meaning, beyond just the surface-level words themselves? This truly feels like something out of science fiction.
It absolutely does, and this is precisely where vector databases and embeddings come into play. They represent a truly revolutionary leap forward. Unlike older relational databases that organize data into rigid tables with rows and columns, vector databases are specifically designed from the ground up to store and retrieve data as vector embeddings.
Okay, embeddings, what are those exactly?
Think of these as vast arrays of numbers, often hundreds or even thousands of dimensions long. Now here's the crucial part, the real genius. These numbers aren't random. They are carefully computed to encode the semantic essence or intrinsic meaning of information. Imagine a multi-dimensional space, far beyond the 3 dimensions we experience every day. In this abstract conceptual space, items that share similar meanings or contexts are positioned very closely together, forming what we call semantic clusters. Conversely, items with vastly dissimilar meanings are placed far apart.
Okay, so distance equals difference in meaning.
Pretty much, yeah. So, to give a concrete example, apple, the fruit, and orange would be neighbors in this vector space because they are both fruits and share deep semantic similarities. But apple, the fruit, and Apple, the company, would be located far apart, reflecting their utterly distinct meanings despite sharing the same word. The key insight here is that meaning is translated into mathematical relationships.
So instead of a traditional search engine just matching the exact word space with every document containing that word, a query like science fiction movies about space could be converted into a vector that's semantically close to, say, 2001, A Space Odyssey, or Interstellar, even if those exact words aren't in the movie titles. That's incredibly powerful.
Precisely. That's exactly how it dramatically enhances relevance. These sophisticated embeddings are generated by embedding models, which are trained on absolutely massive data sets. In the early days of AI, these models were primarily trained on trillions of texts, forming what we called a text corpus. But today, with the advent of multimodal search, these gigantic training databases now include not just text, but also images, video, and audio.
Wow, so it understands meaning across different types of media.
Yes, this vast, diverse training is the foundational bedrock of many large language models, enabling them to grasp and represent meaning across different forms of data. It's building a richer, more nuanced understanding of the world.
But if we're dealing with millions or even billions of these high-dimensional vectors, doesn't comparing every single query vector to every single stored vector sound incredibly slow and computationally expensive? It feels like that would create a huge bottleneck.
You've hit upon a critical challenge, and it's a very insightful question. Comparing every vector directly would indeed be prohibitively slow and expensive, making real-time search impossible. This is where vector indexing employs what are called approximate nearest neighbor ANN algorithms.
Approximate, so not exact.
Right. And here's the real genius. These algorithms make a clever trade-off. They sacrifice a tiny, almost imperceptible fraction of absolute precision in favor of a massive gain in search speed. Instead of finding the exact nearest match every single time, ANN algorithms quickly locate vectors that are very likely to be among the closest matches. Think of it like a highly optimized postal service that knows the fastest, most likely route to your destination, even if it's not the absolute shortest path guaranteed. Examples of these efficient indexing methods include HNSW, which stands for Hierarchical Navigable Small World,
Catchy name.
and IVF, the Inverted File Index. HNS-W, for instance, builds a sort of multi-layered map, much like a city has highways, main roads, and smaller streets, allowing the system to quickly navigate to the right neighborhood of similar vectors. IVF, on the other hand, pre-segments the entire vector space into clusters, so it only has to search within a smaller relevant segment.
Oh, okay. Divide and conquer.
Exactly. This tiny sacrifice in absolute precision unlocks an incredible leap in speed, making real-time semantic search possible on a massive scale. This exceptional efficiency is one of the core reasons we experience the rapid, almost instantaneous responses we see in today's large-scale AI applications and semantic search systems.
AI at the helm, LLMs, and the future of information retrieval.
Okay, let's shift gears a bit. We hear a lot about AI hallucinations, these models making up plausible sounding but totally false information. It's a real concern, especially when we rely on AI for critical information. So how does semantic search help combat that tendency, grounding AI in reality?
This is precisely where the RAG architecture, retrieval augmented generation, becomes an absolute game changer. And it's a direct response to the hallucination problem. The core issue with purely generative AIs is their inherent tendency to invent information that sounds convincing but is factually incorrect. This is, as you noted, an environment where misinformation thrives. RAG was specifically designed to directly combat this by grounding the AI's responses in verifiable external data.
Retrieval augmented generation, RAG. Okay, how does that work?
The RAG process generally involves two main yet highly integrated phases. First, there's the retrieval phase. When you send a query to our Argo system, it doesn't immediately generate an answer from its internal memory or training data alone. Instead, a dedicated retrieval component springs into action. This component performs a semantic search on an external knowledge base, which could be a vast internal company database, a carefully curated collection of documents, or even the entire internet, looking for information that is semantically relevant to your specific query. It represents both your query and the relevant documents as those vector embeddings we just discussed. And the proximity of these vectors in that multidimensional space indicates their relevance to one another. Then comes the crucial generation phase. The most relevant information retrieved in that first step is then fed to the large language model along with your original query.
So it gets context before it writes the answer.
Precisely. The LLM then uses this augmented context, this verified external information, to generate a much more precise, factual, and contextualized answer. It's not just relying on what it remembers from its training, which might be outdated or even subtly incorrect. It's actively looking up current relevant facts to support its response.
That's fascinating. So it's essentially like giving the AI a dedicated on-demand fact checker right before it speaks. It has to base its answer on verifiable current data rather than just its internal, potentially outdated or imagined memory from training. What a powerful safeguard against misinformation. But does this also mean our RAG systems might struggle if that external knowledge base itself is incomplete or contains biased information?
That's a very perceptive question. And yes, it highlights an important consideration. While RAG dramatically reduces hallucinations by grounding the AI, the quality and integrity of the retrieved information are paramount. If the external knowledge base itself is incomplete, biased, or contains inaccuracies, the AI's generated response will inevitably reflect those limitations. So the source material remains critical.
Sure, garbage in, garbage out still applies to some extent.
It does. But to your original point, this process does dramatically limit the AI's potential to invent information from thin air, making its output far more grounded, reliable, and trustworthy. This revolution in search, by widely adopting the RAG architecture, is proving to be a powerful, indispensable tool in our ongoing fight against the spread of misinformation in the digital age, provided the sources are well vetted.
When we interact with these AIs, it often feels like they're really thinking deeply about our questions, almost like they're engaging in a detailed mental process. How sophisticated is this internal process when we pose a query, say, to Google's AI overview?
It's incredibly sophisticated, far beyond a simple keyword match. Take tools like Google's AI overview, for example. They don't just process your query directly in a linear fashion. They engage in what's known as query fan-out.
Query fan-out.
Yeah. This represents a truly fundamental shift in how search works, moving from a single pass to a complex, multifaceted investigation. What happens behind the scenes is that the AI takes your initial query, and rather than just searching for keywords, it breaks it down into a complex network of interconnected subqueries.
Okay.
It then fans out or spreads these subqueries across its vast knowledge graphs and its entire web index to generate rich, synthesized, and comprehensive answers. It's actively simulating a much more rigorous human search behavior, essentially conducting a thorough, multi-pronged investigation before formulating its ultimate response. It's far more meticulous and deeply analytical in preparing its answer than traditional search ever was.
So it's not just a single search, it's a whole branching investigation happening behind the scenes, almost like a team of detectives following multiple leads simultaneously. That sounds immensely powerful for uncovering context.
Precisely. This complex branching investigation is driven by advanced reasoning techniques,
Yeah.
notably chain of thought, chain reasoning.
Like thinking step by step.
Exactly. With CutOT, the AI first thoughtfully considers different facets of the information related to your query, analyzing various types of sub-questions it needs to answer. This includes related queries, implicit questions hidden within your main query, and comparative aspects, literally thinking through the problem. Only then does it generate a diverse set of synthetic fan-out queries. This is a profound step beyond simple keyword expansion. It's a deep contextual decomposition of your original question, driven by an internal reasoning process.
And if the AI is generating these complex, unpredictable subqueries on the fly, it strikes me that traditional SEO tools that rely on predicting keywords or measuring static ranks must really struggle to keep up, right? The game must have completely changed for content creators.
This raises an important question for you, the learner, and for anyone involved in content optimization. You're absolutely spot on. The problem isn't just about trying to optimize for these unpredictable subqueries. It's about accepting that there's no way to rank or even track visibility in traditional terms anymore.
Wow, really? No ranking?
Well, not in the same way. The game has fundamentally changed because these follow-up questions are so deeply contextual and often impossible to predict deterministically. The AI generates them on the fly, based on its nuanced understanding of the initial query and its vast knowledge base. This means the focus shifts from keywords to truly comprehensive, authoritative content that answers a breadth of related questions.
And how does the AI actually read and process a page to perform all this complex analysis and chunking? Is it just looking at the full text as one giant undifferentiated block, or is it more intelligent than that?
Not at all. Google doesn't process content as a single, undifferentiated block. Instead, it systematically chunks documents into smaller, more meaningful pieces. Based on current research and observations, they appear to use a hybrid strategy for this, which has significant implications for how you structure your content.
Okay, what kind of strategies?
First, there's fixed-size chunking, primarily used to adjust content to fit the specific token limits of models, like the 2048 token limit for Gemini embedding 001. Then, for unstructured text, they use recursive chunking, which breaks content down progressively, first by paragraphs, then sentences, and finally by individual words.
Makes sense.
Crucially, there's also semantic chunking, where phrases or sections that are semantically related are grouped together, regardless of strict grammatical boundaries. This helps the AI understand core ideas. And perhaps most importantly for content creators, there's layout-aware chunking.
Layout aware, so based on how the page looks.
Exactly. This method segments content based on its underlying HTML structure, recognizing headings, H1s, H2s, lists, tables, and other visual and structural elements. This last one is particularly significant because it mirrors how humans visually process documents and how Google's AI determines relevance at a granular passage level. The key takeaway for you is that a well-structured document designed for human readability and clear hierarchy is also much easier for the AI to ingest and understand effectively.
Library science, the ancient roots of modern AI search.
It's truly amazing how cutting-edge AI technology, with all its complexities, is drawing on principles that are, in some cases, centuries old. Where do these foundational ideas about organizing and retrieving knowledge actually come from?
This is precisely where the venerable field of library science provides invaluable and surprisingly relevant frameworks. The very concept of an acervo, which refers to a collection of organized documents available for study, research, or leisure, translates almost directly to the vastness of the modern web.
Huh, a servo. Never heard that before.
It's a library science term. The internet, in essence, is the largest, most sprawling library in the world. And like any good, functional library, it needs to be carefully curated, diverse in its offerings, well-indexed, and constantly updated to remain useful.
And this connection to library science, it's not just theoretical, is it? It sounds like there are concrete historical figures whose ideas are now more relevant than ever, almost like blueprints for our digital future.
Not at all theoretical. A key figure here is Shyali Ramamrita Ranganathan, often revered as the father of library science in India. His 5 Laws of Library Science, published way back in 1931, are remarkably prescient and surprisingly applicable to our digital age.
Wow, 1931. What are these laws?
Let's look at them. 1. Books are for use. The core insight here is that content exists to be consumed and to facilitate knowledge, not just to sit on a virtual shelf. For the web, it means content should be accessible, engaging, and genuinely utilized by users.
Okay, makes sense. Usefulness.
Yep, every reader has their book. This emphasizes the importance of understanding user needs and profiles. The nugget is that content should be tailored or discoverable to perfectly match what individual users are looking for, a precursor to personalization.
Personalization, right?
Every book has its reader. This points to the discoverability and dissemination of content. The insight is that even if the perfect piece of content exists, it needs effective mechanisms to be found by the right person.
Discoverability, got it.
4. Save the reader's time. This highlights that efficient organization, clear navigation, and effective retrieval systems are paramount. The takeaway is that users shouldn't waste time sifting through irrelevant information. Their time is valuable.
Efficiency. Crucial in line.
5. A library is a growing organism. This recognizes that knowledge is dynamic and ever-expanding. The key here is that content must be continuously updated, managed, and expanded to remain current, comprehensive, and valuable.
So how does this truly timeless wisdom translate directly to our current deep dive into semantic optimization for AI? What are the modern equivalents of these laws for SEO practitioners and content creators?
We can adapt these laws quite powerfully for SEO in the AI era. Instead of every reader has their book, we can say every visitor has their content, emphasizing hyper-personalization and matching content to nuanced user intent. Save the reader's time directly translates to optimizing for a seamless user experience, incredibly efficient site architecture, fast load times, and providing direct, concise answers, maybe via AI overviews. And a library is a growing organism becomes a site is a growing organism, highlighting the need for continuous content updates, rich semantic enrichment, and proactive technical maintenance. It profoundly underscores the importance of truly understanding the user and structuring information thoughtfully, systematically, and with long-term dynamic growth in mind.
With these foundational principles now etched in our minds, what specific tools or methodologies from library and information science are helping us organize this vast digital library for AI, making it truly comprehensible to machines and therefore more useful to us?
Several powerful tools emerge from information science. One is domain analysis.
Domain analysis, what's that?
In information science, this is a fundamental methodology to deeply understand the knowledge organization within specific fields. It delves into the core concepts, the foundational theories, current research trends, communication patterns among experts, the social structures that validate knowledge, the specialized language and terminology unique to that field, and its historical evolution. It's a holistic, almost anthropological approach to understanding a knowledge ecosystem. For you, the learner, this means if you're optimizing, say, a dental clinic's website, you absolutely need to conduct a thorough domain analysis of dentistry. This involves not just common procedures, but its specific technical language, the relevant regulatory bodies, the core concepts that underpin dental practice, and even how dentists communicate about new research.
So really getting into the weeds of that specific field.
Exactly. This rigorous introspective research allows you to build a robust and authentic semantic foundation for your content, which AI can then accurately interpret and trust. The key insight is that real expertise shines through specific domain language.
Okay, let's unpack this a bit more. Once you understand the domain, how do you make sure everyone, both humans and machines, is on the exact same page with terminology?
Yeah.
Human language is so flexible, with synonyms and different ways to say the same thing.
That's where controlled vocabularies become indispensable. These are essentially carefully curated lists of authorized terms. They come with clear rules about which terms are preferred over others, especially when dealing with synonyms or closely related concepts.
Like a style guide for words.
Kind of, yeah. For example, a controlled vocabulary might stipulate that running shoe is the preferred term, even if users might search for running slipper or jogging footwear. The system is then designed to map those alternative terms to the preferred one. This creates a consistent semantic layer between the diverse ways a user might phrase an input and the precise terms used in the system's database, significantly reducing that costly ambiguity we talked about earlier.
And how do we structure the actual content on a website for these sophisticated systems? How do we move beyond just individual pieces of content to an organized, navigable whole, rather than just a jumble of pages.
This is where taxonomies play a crucial role. In essence, taxonomies are explicit data models specifically designed for unstructured text. They are hierarchical representations of how humans naturally organize information.
Hierarchical, like categories and subcategories.
Exactly, creating logical classifications through categories and subcategories. A well-constructed taxonomy acts as an intuitive, logical map for search engines and AI agents. It maps out a site's content and establishes clear hierarchies and relationships. For example, semantic SEO would logically be a subcategory of SEO, which itself falls under digital marketing. This provides clear, machine-readable context about the relationships between different topics, making your content more discoverable and understandable.
So, taxonomies organize content into hierarchies. But what about defining the relationships between concepts in a much more intricate way? Like, how does a director relate to a film or a customer to a product? That seems more complex than just parent-child categories.
That's the realm of thesauri, and even more powerfully, ontologies. A thesaurus is a controlled vocabulary that explicitly includes semantic relationships between terms, like broader terms, narrower terms, and related terms. It enriches the connections, showing how concepts are linked. But an ontology is even more formal and comprehensive. It's defined as a formal, explicit specification of a shared conceptualization.
Okay, this sounds pretty academic. Break that down for us.
Right, it sounds dense, but this precision is exactly what allows an AI system to understand the true meaning of, say, your company's product catalog. It's not just listing items. It knows that product X is a type of software that solves problem Y for customer Z. It defines everything with absolute precision. Classes or concepts like vehicle, individuals or instances, which are specific examples of classes like a Tesla Model 3. Properties or attributes and relations that describe characteristics, for example, has wheels, or connections between entities, example, is manufactured by. Axioms, which are formal rules or statements considered true within the domain, like all humans are mammals.
Rules, got it.
And hierarchies, like car is a subclass of vehicle, indicating that a car is a type of vehicle and inherits its properties. This complete structure allows for incredibly rich and unambiguous knowledge representation.
What's truly fascinating here is how these highly formal ontologies specifically help AI, especially large language models, move beyond mere language processing to genuine understanding. How does that connection work?
They're absolutely central. Ontologies provide the semantic schema, essentially the grammar and dictionary for a domain. They allow machines to truly understand context, not just raw data. This structured understanding enables several critical AI functions. Firstly, they enable sophisticated reasoning, allowing AI systems to derive new knowledge from existing information based on the defined rules.
So it can figure things out.
Yes, infer new facts. Secondly, they significantly improve the explicability of AI decisions, what we call XAI, providing a traceable logic for why an AI made a certain conclusion. Thirdly, they power genuinely semantic search, moving far beyond keyword matching to understand the user's true intent. Finally, they ensure interoperability between complex systems and agents, facilitating consistent communication and information exchange. Critically, for large language models, ontologies act as a stable anchor, guiding their generation process and significantly reducing hallucinations by grounding them in validated, structured facts from the domain.
And then there are knowledge graphs, KGs. We hear that term a lot, especially with Google. How do they fit into this picture with ontologies? Are they the same thing, or are they different aspects of this semantic understanding?
That's a great question. They're intimately related but distinct, and it's a common point of confusion. An ontology is the schema or structure. It defines the rules, the classes, and the properties that govern a domain. Think of it as the grammar of a language.
The blueprint.
Exactly. A knowledge graph, on the other hand, is the data plus structure. It's where you store and organize specific instances and facts according to that ontological model. So, if the ontology is the grammar, the knowledge graph is the actual text written using that grammar, populated with real-world entities and their relationships. Knowledge graphs, at their simplest, are just a massive collection of individual facts, each stated as a little mini-sentence we call a triple.
The triple.
Yeah, subject, predicate, object. Think of it like a very precise game of who did what to whom. So, Yuri bought iPhone isn't just data, it's a complete understandable relationship that a machine can immediately grasp. And multiply that by billions of facts, and you have a Google knowledge graph. Google's own knowledge graph, for instance, was initially built by extracting structured information from sources like Wikipedia info boxes. They use advanced techniques such as entity linking to unify different mentions of the same real-world entity, schema alignment to standardize attribute names, and data fusion to consolidate different values for the same attribute. These KGs are the powerful force behind conversational AI systems like Siri and Alexa, providing them with the deep contextual information needed to answer complex queries accurately.
The Semantic SEO playbook, practical applications in the AI era.
So given all this fascinating development for an SEO professional, or really anyone creating content for the web, how do we practically optimize for this new AI-driven search world? What's the practical playbook for navigating this semantic shift?
Well, the shift from traditional keyword-focused SEO to semantic SEO is not just critical, it's already profoundly underway. Since Google launched its knowledge graph way back in 2012, search has fundamentally moved to an entity-based approach. The algorithms now actively try to understand the meaning behind your query and the content, not just the exact words. This means optimization is no longer about tweaking algorithms with keyword density or superficial tricks. It's about optimizing for machine understanding.
Machine understanding.
Yeah, it's about helping the algorithms, the large language models, and AI agents to comprehend, reason about, and effectively present your content, often in a hyper-personalized way, to the right user at the right time. Your goal is to make your content unambiguously clear to an intelligent machine, almost like you're writing a meticulously organized instruction manual for AI.
That makes perfect sense. So if we want our content to be unambiguously clear to an intelligent machine, what's a concrete first step for someone wanting to get started with this practical application? Where do you begin?
A foundational and often overlooked step is using structured data, specifically employing standards like schema.org.
Schema.org markup.
Exactly. This isn't just a recommendation anymore. It's essential for clear machine understanding. Structured data provides explicit context to your content, telling search engines precisely what your data means. For example, if you have a recipe, schema.org allows you to mark up ingredients, cooking time, reviews, nutritional info in a way that the machine instantly understands this number is the prep time, this list is the ingredients.
Right, no guesswork.
Precisely. This enables rich snippets in search results, giving users immediate, detailed answers directly on the search page. For small businesses, this is a massive competitive advantage, as many still don't leverage it, despite its power to provide direct answers and help your content truly stand out from the noise.
And what about the content itself? Beyond just marking it up with structured data, what's the fundamental shift in how we should be writing or creating content to speak the AI's language?
The content strategy moves significantly away from keyword stuffing, which, let's be honest, was always a poor practice anyway, to building a rich semantic field around your core topic.
Semantic field, like related concept.
Exactly. If you're writing about mango, the fruit, your text shouldn't just repeat the word mango over and over. Instead, it should naturally include a vibrant network of semantically related terms like tropical fruit, juice, vitamin C, sweet, seed, peel, maybe even the specific varieties or growing regions. This rich network of correlated terms provides the algorithm with abundant context to disambiguate the term, ensuring it knows you're not talking about a clothing brand or something else,
Right.
and to understand your document comprehensively.
This approach sounds like it naturally aligns much better with genuine user intent, providing a more satisfying and complete experience for the person searching, because you're answering a broader range of their potential needs.
Absolutely. By focusing holistically and deeply on the topic, you naturally answer a broader range of related questions that a user might have, from generic queries like what is mango to more specific ones such as health benefits of mango or how to cut a mango. This comprehensive coverage demonstrates true expertise and authority within your domain. This is also precisely why Semantic SEO often advocates for content creators who are genuine experts in their domain. When someone with a background in finance writes about investments, they naturally use the specific, nuanced language and concepts of that field.
They know the jargon, the concepts.
Exactly. This authentic domain-specific vocabulary and rich semantic field are what algorithms like Google's BERT, MUM, and now Gemini are designed to understand and value, making your content more trustworthy and relevant.
Beyond individual articles, how do we structure an entire website for semantic success? What's the starting point for building this robust semantic foundation for a whole digital presence, rather than just optimizing individual pages in isolation?
It fundamentally starts with domain modeling. Before you write a single line of content or design a single page, You need to conduct extensive research to identify the precise knowledge domain your site belongs to and define its central entities. This isn't about externally chasing what keywords people are searching for. Instead, it's an introspective process.
Introspective? How so?
It's about understanding what your business wants and needs to say to the world, what unique value it brings, and what its core expertise is. This internal understanding forms the bedrock. For example, if your project is a law firm, you would first define law as your overarching domain, then identify all its core concepts like family law, civil rights, litigation process, judgment, etc., and crucially, how your firm specializes and provides value within that specific legal landscape.
So once we've meticulously modeled the domain and understood our core message, what comes next in building out the semantic structure for the website? How do we then organize all that content effectively?
You then proceed to build out your controlled vocabularies and taxonomies. These are absolutely crucial artifacts for guiding consistent content creation across your entire platform, structuring your site's navigation, and significantly enhancing search engine understanding. A well-structured taxonomy acts like an intuitive, logical map for search engines and AI. It establishes clear hierarchical classifications, categories, and subcategories, and explicitly reveals the relationships within your content.
Like your blog example, right? Semantic SEO under digital marketing.
Exactly. That explicit hierarchy reinforces the meaning and context of the content for both human users trying to navigate and algorithms trying to understand your entire knowledge base. It makes everything easier to find and comprehend.
And how do these tools-controlled vocabularies and taxonomies specifically help with the AI's chunking process that you mentioned earlier, where it breaks down documents into smaller pieces for understanding?
They are absolutely essential for that, because Google's AI utilizes layout-aware chunking and semantic chunking, a site that is built with well-defined taxonomies, clear headings, using proper HTML, H1, H2 tags, etc., and robust structured data, like schema.org, is immeasurably easier for the AI to ingest, parse, and understand.
So good structure helps the AI read better.
Precisely. This semantic clarity and structural integrity make your content far more likely to be retrieved and cited by AI agents as a foundational source for their generative answers, because the information is pre-organized, explicitly linked, and it's easy for the AI to pinpoint relevant passages accurately.
This also sounds like it would be incredibly helpful for internal search functions on a website, which can often be frustratingly ineffective. Many of us have probably typed in a term only to get no results found on a site we know has the information.
This raises an important question, and you're spot on. The current state of internal site search on many websites is, frankly, often inefficient and leads to poor user experience. Interestingly, librarians are actually the most qualified professionals to optimize internal search.
Librarians for site search. That's interesting.
Yeah. By thoughtfully combining large language models, knowledge graphs, and traditional search engines, for example, through a RAG architecture specifically for your internal data, you can create incredibly powerful and highly qualified internal search experiences. A well-designed taxonomy, for instance, can ensure that if a user types running shoe into your e-commerce site's search bar, the system understands that it means tennis shoe or trainer, based on your controlled vocabulary, and delivers a list of relevant products, rather than the all-too-common and frustrating "no results found" message. It bridges the vocabulary gap within your own content, making all your information more accessible.
What about the long-term benefits of this semantic approach? Does it offer a more enduring advantage than constantly chasing algorithm updates with traditional keyword-focused SEO tactics, which can feel like a treadmill?
That's one of the most compelling advantages of semantic SEO, its inherent permanence. Unlike volatile keyword-based strategies that can fluctuate wildly with every algorithm update, projects developed with a robust semantic technique consistently show sustained improvements in impressions and clicks over time.
Sustained, even without constant new content.
Yes, this even happens if content updates aren't continuous, as evidenced by case studies where sites continued to grow in visibility even after content creation paused for a period. It's not a quick fix. It's a strategic investment in long-term visibility, authority, and true understanding by the search ecosystem. It creates a resilient digital asset that compounds in value over time.
Navigating the semantic future human-AI partnership.
This all points to a fascinating future where humans and AI work together in a much more integrated way.
Yeah.
But how do we, as humans, ensure we're getting the absolute best out of these incredibly complex AI systems? It's easy to feel overwhelmed, wondering if we're even asking the right questions.
The concept of the reference interview from library science is absolutely key here, and it's experiencing a powerful resurgence as a model for interacting with AI.
A reference interview.
Hmm.
Like when you ask a librarian for help.
Exactly. Traditionally, a librarian helps a user articulate their real information need, especially when the user isn't quite sure what they're looking for or how to phrase it. This iterative process of asking clarifying questions is indispensable for narrowing down broad inquiries and identifying the true intent. We can apply this directly to interacting with modern AI agents like Google Gemini. Rudyard Kipling's famous 6 Honest Serving Men, what, why, when, how, where, who, offer a perfect, timeless framework for structuring your prompts and queries to AI.
What, why, when, how, where, who.
Okay. Transforming vague questions into precise commands. What? Define the core topic or entity you're interested in. Why? Clarify your ultimate purpose or goal. Are you looking for data for a comprehensive report or just trying to understand key trends for a personal project?
The purpose matters.
When? Specify the relevant timeframes, such as latest research from 2020, 2025, or historical data up to the 1990s. How? Define the desired output format, depth, and style. Do you want a detailed analysis, a comparative table, a summary, or bullet points?
Format and style, right.
Where? Specify any geographical or domain limits, like Brazilian market, academic sources only, or focus on renewable energy in Europe. Ooh. Assign a persona to the AI, e.g., act as a senior molecular biologist, and consider who the information is ultimately for, e.g., for a non-technical audience. It's a complete conversational framework.
So instead of a vague and open-ended prompt like, tell me about solar energy, we'd use this framework to build a rich, structured query like, act as a market analyst, provide a detailed analysis of the Brazilian residential solar energy market from 2023-2025, focusing on installation costs and ROI for the top 3 photovoltaic technologies for a stakeholder report. That's an enormous difference in precision and expected output. How truly game-changing is that for finding what we really mean?
It's an enormous difference, and it illustrates the power of this human-AI partnership. This iterative, almost conversational dialogue where you co-produce the search strategy with the AI is how we transform generic, often ambiguous questions into precise, efficient, and highly relevant queries. It's about leveraging human intelligence and our understanding of context to guide and amplify the immense computational power of AI, making the AI truly your personal, very knowledgeable reference librarian.
When Google's AI systems process information and generate answers, what does it value most from a content perspective? What makes a piece of information trustworthy and useful in the eyes of the AI, guiding its selection process?
The Google Search Quality Evaluator guidelines provide incredibly clear insights into what AI systems and the human evaluators training them prioritize. At its core, it comes down to relevance, authority, and reputation, which are the fundamental elements encapsulated in the EEAT framework: experience, expertise, authoritativeness, and trustworthiness.
EEAT.
Relevance is straightforward. It ensures that the results presented by Google truly match the user's intent, whether they're looking for a specific piece of information, a particular website, a product, or a physical location. Then there's authority, which refers to the extent to which the content creator or the website itself is recognized as a trusted and reliable expert on a given topic. Different topics, of course, demand different levels and types of expertise. An authoritative source is seen as a go-to for accurate and useful information.
Being the recognized expert.
Exactly. Finally, and crucially, there's reputation. This is about how external, independent sources perceive the site or content creator. This involves looking for mentions in news articles, references from other experts, and credible recommendations from third parties. What does the rest of the web think of you?
So building a strong, verifiable reputation and consistently demonstrating genuine expertise becomes even more critical for AI to trust and, importantly, cite your content as a reliable source. It's not just about what you say on your own site, but who vouches for you and how you're perceived by the broader ecosystem.
Absolutely. Reputation in particular is extremely important for detecting unreliable sites and creators. Even if content appears superficially good, a strong negative reputation discovered through independent research can expose scams, fraud, or other signals of harm. That can lead to a lowest quality rating from evaluators and thus a very low trust signal for AI. These three elements, relevance, authority, and reputation, are fundamental for quality evaluators. By extension, they are deeply ingrained in how Google's algorithms are continuously refined. Providing accurate, reliable information from authoritative and reputable sources is the direct path to user satisfaction and, critically, to achieving visibility and citation by AI agents.
It sounds like we're moving towards something truly ambitious. A global, interconnected database that both humans and computers can easily understand and navigate, like a universal brain for information. Is that the end game?
That is precisely the grand vision of the semantic web, a concept spearheaded by Tim Berners-Lee, the inventor of the World Wide Web itself.
Ah, the man himself.
Yes. It's conceived as an extension of the current web, where information isn't just displayed for human consumption, but is given a well-defined meaning, making it perceivable by both humans and, crucially, by computers. The ultimate goal is to interlink the meanings of words and data so that machines can understand content with a depth akin to human comprehension, fostering a truly intelligent global network. This ambitious undertaking involved constructing complex layers of metadata, logic, and security, utilizing powerful technologies like RDF, Resource Description Framework, for data modeling, and OWL, Web Ontology Language, for defining those precise ontologies we discussed.
RDF and OWL, more acronyms.
Essential ones for this vision. The aim is to move beyond what Berners-Lee famously called a web of documents to a web of data, where search is truly independent of type, format, or source. The results would be rich with semantically interrelated information, providing comprehensive answers rather than just a list of disconnected links, creating a vast, interconnected tapestry of knowledge.
That sounds like a colossal undertaking. Is this semantic web ready for prime time yet, or is it still more of a long-term goal that we're slowly building towards?
Well, while significant progress has indeed been made over the years, and many components are already in use in various ways, many of the underlying technologies still require further development, integration, and standardization to reach their full, unified potential. It's not quite there yet as a complete system.
Still a work in progress.
Definitely. However, the journey is accelerating rapidly, driven by the dramatic advancements in AI, machine learning, and the widespread adoption of ontologies and knowledge graphs we've been talking about. Pierre Levy's vision of a global hypercortex coordinated by a computational metalanguage. Well, with each passing year, it's becoming a more tangible and achievable goal, moving from abstract theory to practical implementation before our very eyes.
Wow. We've journeyed from the frustrations of traditional keyword search to the intricate world of vector embeddings, explored how AI models like Gemini are deconstructing our queries with incredible sophistication, and discovered how timeless principles from library science are guiding the creation of a truly semantic web. It's been quite the ride through the future of information.
It really has, and what's abundantly clear, I think, is that the future of search, and indeed our interaction with knowledge itself, is fundamentally a profound human-machine partnership. Your ability to think critically, understand context, and articulate your needs with precision will be immensely amplified by the sophisticated intelligence of AI. It's not about AI replacing human intelligence, but empowering it, allowing us to access, synthesize, and create knowledge in ways previously unimaginable, pushing the boundaries of what's possible.
So as we step into this new era where knowledge is not just searched for, but understood and generated by machines, think about this. If knowledge is power, and AI is dramatically changing how we access and synthesize that knowledge, what new possibilities and perhaps new responsibilities does that unlock for you in your personal and professional life?